lovely to see you all. My name's Jane Hart, and I'm going to, and this is Michael Seaborn, and I'm going to introduce a session for you this morning. What we're hoping to do is show 100 years of technology improvements and ideas for the future. And the idea of this session is to get a range of whole of Earth and space sciences, so we can really see how the subject has changed and all the integration between the different subjects. So we're going to start today with M. Little, who's going to talk about computational technologies.
Good morning, everyone. I don't have slides because I couldn't get them through export control at NASA, so I'll just talk, and I'll offend them, but they won't know that I'm offending them. So thank you for coming this morning. It's really kind of funny. I mean, here's a room that holds, what, 1,000 people or something like that. And the NASA Town Hall they were turning people away because of the overflow. So I want to talk for a few minutes about several themes related to NASA's experience with supercomputing and also with computing in general, but also challenge you to think about some things for the talks that you're going to hear after mine. NASA has spent a long time doing investments in computational technologies in one form or another. NASA doesn't generally invent new technologies, but we find new ways to use the existing technologies. So I have my notes, so I have something to talk about. But I do want to talk, to start with, tell you some stories. And I told Mike Seaborn that he really ought to have Jerry Pournelle or Larry Niven give this talk, not me, because they're far more imaginative than me. But I want to start with some things that NASA's done to sort of give you an idea of how this has worked over the last 70 years. And then talk a little bit about some of the challenges for the future activities that in the Earth Science Technology Office we see the direction that NASA needs to go. So the first thing I want to talk about is a friend of mine, John Lynn, who was the first Nasa Cio. But John has the distinction of being one of the few people in computer science that Wernher von Braun actually was willing to hire. And von Braun, if you think back to the late 40s and the 50s, when von Braun was doing rocket tests out of Kennedy, they had a bunch of paper recording machines that would produce, a mile and a half of paper. And so they were measuring each of the parameters on these machines, and they'd have time steps on them, and they would spit out about a mile and a half of paper, and then they'd go to a hangar and they'd lay out 25 lines of paper, and they'd have engineers crawling across each one of those, and at the different time steps they'd record the data, and then they'd compile all that data into a notebook, a physical notebook, not a Zeppelin or Jupyter notebook. And they would then do the calculations from this. And of course, every time they did a rocket test, and they even ran the engines and they recorded data, this is a very time-consuming process. So von Braun, being interested in moving the space program ahead, heard about this new IBM computer, that he had some familiarity with IBM from his previous life, and got himself an IBM 360, but it didn't run long enough to do the result, to do all the calculations. It would crash on a pretty regular basis. Actually, the timing was about 30 minutes. Every time they'd start it up, it would shut itself down in about 30 minutes. So von Braun hired John Lynn, who had just graduated with his PhD from the University of Alabama at Huntsville, to figure out what was wrong with the IBM 360, fix it, and so that his rocket program could move ahead. And it took John about 6 months, and by the time he was done, he and his team essentially rewrote the System 360 operating system, which, does anybody in the room here besides Milt ever have any experience with the IBM 360? Okay. So, anyway, that's great. It was a very good computer, but it pretty much ran very, in a sequential way, very slowly. And, but it was much better than this other approach that von Braun was using to do all these calculations. So John fixed the the operating system, turned everything over to IBM. IBM revised their operating system and started being more successful commercially because of that. This is an example of the way that NASA has been working since, somewhere in the 1940s in its predecessor form. And we've done that a number of different times. Another example of that is with the Cray Supercomputer, CDC, the Cray Supercomputer, SGI, all of these companies have benefited by their relationship with NASA. And to a large extent, that relationship has been because we've been a very demanding customer. We don't let them do crappy software engineering. We don't let them, sell us, at least, computers that don't work very often. And if we find that we've acquired those, we fix them. And we did that with SGI, and SGI in the late 80s had a really magnificent workstation that was great hardware, but it didn't work very well. And it was hard to use, and they were using a proprietary operating system. And the guys at NASA Ames, at the computer center at NASA Ames, convinced SGI to use Unix for that operating system, and they did a specific flavor of Unix in order to do that, and it worked great. And the irony, of course, is during the first Gulf War, the intelligence community was buying all the SGI workstations so they could do visualization of the battlefield, and NASA couldn't buy any at the time. So we had like an 18-month backlog before we were actually able to start taking deliveries of SGI workstations again. This is, kind of typical of the way we've experienced things in dealing with the commercial world and advancing the technology, not because we're necessarily inventing it, but we're making it better. And we're making it, in some cases, we're actually making it successful. Other government agencies and our friends in Europe and Japan have been doing exactly the same thing. It's been really over the last 50 years, the bunch of us kind of pushing the commercial firms who come up with a great idea, they come up with a great implementation, but they need some demanding applications to work on that. And that's kind of how we've worked, and I think that's probably a successful model for an interaction between a government agency and commercial providers of equipment and so on. The internet, I'll only say for a minute that NASA, of course, was part of the US government consortium that helped develop the internet, and I remember the conversation in the early 90s with Joe Bredekamp, who was the NASA representative on the Internet Advisory Council, about whether or not we should allow commercial traffic on the internet. We were spending approximately, so I was in what used to be called Code R and funding the data communications capabilities, and we were spending about $10 million a year on a T1 line from Ames to Langley across the country. And we got to the point where we just couldn't afford the data communications capacity that we needed in order to make all the different computers work together, and decided that, along with everybody else, that commercial traffic was necessary. And of course, we were joking about, what are the implications of this, the unforeseen consequences of this decision. And, I had lunch with Joe Bredekamp about 3 years after it became commercial, and after he was still at NASA headquarters. And the conclusion we came to is we didn't realize that we'd have 10 million high school students trying to break into our computers all of a sudden. And of course, the rest is history. So let me talk for just a minute about the future of this relationship between us and the commercial companies. You'll hear more about some of the experiences in specific science disciplines as the morning progresses. But I just want you to be thinking about what in ESTO we're describing as a new observing strategy, which is essentially constellations of instruments that are at different vantage points, making measurements of phenomena and trying to observe in an integrated way these phenomena like tornadoes or tropical storms transitioning into hurricanes or things like that. This is going to require a completely different set of computational capabilities than we have today that look much more near real time. And in particular, the command and control loop, if we move to an autonomous observing system, then the command and control loop for that, what comes out of the instrument and tells the control loop, the control system, where to go look and to get the other instruments on other satellites to look at the same location. These are pretty complicated systems. Let me also emphasize that computer security, unlike what Joe Bradykamp and I and the other people involved in the early days of the internet, where we just we didn't have to make any assumptions because we restricted who had access to it. But once it becomes more accessible to other people, computer security becomes a much more significant concern, and that's one of the things that we're concerned about in ESTO and the AIST program is how do we secure these assets so that they work in an autonomous way for the people who designed and built them, not for somebody else, not for 10 million high school students to take pictures of the Playboy Mansion or something. So these are some important considerations that we need to think about, including two more that I just want to draw your attention to. One is, what is the role of humans in a autonomous system or a semi-autonomous system? So we've seen this problem with the 737 MAX, the Boeing aircraft. We've seen this problem with self-driving automobiles. We've seen this problem if you're spend time in Washington. The metro system had a really significant accident a few years ago. And actually, there's a number of train accidents that are caused by this, where the trains are operating in an automatic mode, but the operator is texting, somebody or reading or doing something where they're distracted because everything's going normal. So, with these autonomous systems, things go just fine until they don't, and it's very difficult to predict when they're not going to go just fine. So there's a significant amount of research that needs to be done that's part psychology and part computer science on what's the role of humans in an autonomous system. The second area that I want to draw your attention to is how do you compare multidimensional data systems or multidimensional data products? If you are comparing two different models against a set of observations, how do you decide which model is doing a better job of forecasting the future? This is, typically when you listen to the weather forecasts on the East Coast anyway, they say, here's the, for hurricane tracks, they say, here's the collection of hurricane tracks from all the different models. And of course, the European model is better than the American model. And then they say, so that's where we think it's going to go. Well, what does that really mean? I mean, what does it mean that the European model is better than the American model? And there's a considerable amount of research that's being done today on how you make a meaningful comparison of those different kinds of different kinds of multidimensional data products. So I'd like to ask you all during the next hour and a half or so, as you listen to these talks, ask yourself those questions. Where's the future of these kinds of problems? What is it that we need from the computational technology in order to actually make this an effective and near real-time solution to, how do we analyze the data and draw scientific conclusions from it? And what is the role of human beings in this kind of an analysis? So with that, I'll let you get on with the actual interesting part of the program. Thanks.
Right. We've got time for a question. Has anyone?
Well, wait a second.
Yeah.
I was under the assumption you guys were still asleep.
So has anyone got a question for got a question there.
Yeah.
So you mentioned the need for security. I guess one of the most fundamental questions is, do you decide to connect the system to the internet, right?
Yeah.
Like, would you do that? And if so, then that changes what kind of security is, right? If not, you don't have to worry about a lot of things.
Well, I believe that if you turn on a computer system, whether you think it's connected or not, it is. And the only way to have it not connected somehow, and potentially it's covert, but the only way to have it not connected is have it not powered up. Back in the good old days when they only had Ethernet connections, you could at least pull the Ethernet plug, but you can't do that anymore. A lot of it's built into the chips even. So I will say that this may necessitate a re-architecture of the way we do intercomputer communications, including a separate internet that is far more restrictive in terms of who actually gets to get on that system. At NASA, we sort of gave up the idea a long time, well, at least those of us in the science and information technology community gave up the idea that a air gap between two networks means it's secure, because somebody will always find a way to interconnect them. So there was another question as well. Yes, sir.
Yeah, Mike. I had a study that talking about the future of NASA computing and whether or not we can custom design a computer specifically for us for our mission, right?
Right.
The vendors came back and say, well, they like to participate, but the cost, the opportunity cost is so huge, their contribution may be limited. Okay, the opportunity cost is really, they have to take away some of the experts who can design the system to put on our problem. So they can make money if they stay on their current path.
Right.
So some of us actually think about all of our space missions, rockets, space flights, and instruments. All of those are one-off systems. And we can, now NASA knows how to do one-off systems.
Right. Yes, we do that quite well.
How we make this happen in the current NASA environment?
So I would just offer that this is really an economics problem, and that I think you're absolutely right. I think a lot of the things we're going to have to do on orbit are going to be unique to the individual mission. And because of power restrictions and all the rest of the stuff, we may not be able to just buy a general purpose processor. We thought with the high performance spaceflight computer program that the Space Technology Mission Directorate was running for NASA, we thought that might be a candidate, but that turned out to be just a bust. So I think that one of the things we're going to have to do is find a smaller company that's prepared to deal with system design in a way that's economic as one-offs. And I think that's actually possible. We've done a lot of that kind of stuff in other areas, but you know, if you want to run 50 million chips and sell them also to Ford to run their automobiles, then you have a different problem than you do if you're building one-offs. And I think it's possible to do one-offs, but just not with the companies that are, you know, making chips today and designing the interfaces and things like that. I don't think Intel would have any reason that they would have an interest in that, and NVIDIA as well, and AMD. I think it's going to have to be some small shop that does this. Let me just mention, and I know I'm running over.
Oh, I think we're going to have to talk about this later.
Prototype shops in Detroit that build cars would be a good model for that.
Right, thank you very much. Right, and now we're going to move on to looking at the ocean with Deborah Kelly.
So this is kind of intimidating to talk about 100 years of ocean sensing in 10 minutes, but we'll get there. So are you sure this is the guy? There it goes. It's delayed. Okay. So, you know, we first started we've been going to sea for a long time, and the early ships from around the Albatross ended in 1920. It was fueled by coal, and now through NSF and the Navy, you know, we have global class research ships of different sizes and more coastal boats that go out, and they're almost all connected to the internet through satellites now. When I first started going to sea, we would get maybe a fax once in a while or something. But now everyone comes out with computers and stay out for 6 weeks at a time, and they have lots of in situ sampling devices and sonar, so it's much more capable ships, obviously. In 1934, the record was set by Beebe. They basically went down in this little sphere. They bolted them inside. And the reason that they were limited to 932 meters is they ran out of cable. And they only were able to sit on the bottom for about 5 minutes or near the bottom. Now we have capable vehicles like the Shinkai and soon to be the third generation of Alvin that'll go 6,500 meters water depth with extended periods. We also have like the human-occupied one where James Cameron went to the bottom of the Marianas in a single vehicle there. Nereus was in 2009, reached the bottom of the Marianas Trench. It was run on a microfiber that allowed it to have communication. It was actually a fiber that was developed to keep track of torpedoes, but they used it for Nereus, which is unoccupied, to go to the bottom of the Marianas. So these vehicles are developing rapidly for different applications. Around 2005, well, in early 2000s, we started using remotely operated vehicles more. They're different in that they're connected to the ship by a fiber optic cable, so they can run 24 hours a day until the mission is over or if something breaks. So we use those routinely. The ones that are designed for cabled observatories have a lifting weight of about 4,000 pounds. The other transformation is that around 2005, we started using high bandwidth, actually transmitting HD video from the ROVs in real time up to the ship and then up to satellite, reaching a global community. So in 2005, we ran a program where the entire science party from, this is the Lost City hydrothermal field, has the largest chimney ever found. It's all carbonate. We ran the entire mission from the University of Washington through telepresence to the ship. And what that allows people to do is you can get a lot more people involved in the science and education program than the 30-some bursts on a ship. Also in the development now is there's a lot of different AUV capabilities that are designed for specific missions, and some of them, like the one that Mbari has developed, if you use low power, it can go for thousands of kilometers. New advances include things like in situ flow cytometers that they're building, mass spectrometers, so they responded to the BP oil spill, so a lot more instrumentation. And the second development has been for gliders, which are buoyancy-driven instruments, and they also are adding instruments depending on what the mission is and can stay out in the water, and they basically go up and down through the water column, providing a 3D image of ocean parameters. Sentry is a little bit different. It was designed specifically, well, one of the main goals was it's an AUV, and it was designed, its missions were dominated by seafloor mapping, but also the discovery of hydrothermal vents. So it's a smart vehicle that can look for perturbations in the water column and hone in on the vents, and many of the new vent fields have been discovered using those techniques. We've certainly come a long way in terms of ocean imaging, where they used to take a line and lower it down to the bottom by hand to figure out how deep the water was. 1977 was a big event, one of these first maps of the world, and this was really detailed. Some of it was kind of made up. But it was really our first view. That was about the same time that plate tectonics was coming as a new paradigm. And this transformed our view of the oceans. In 1997 was the first C-beam map, and so it could image something like the size of this building. And now we have very, very high resolutions where the newer ones are up to 1,600 individual beams with a very large swath width of about 40 kilometers. So really starting to get maps of the ocean that are useful. We probably have imaged in detail maybe less than 5% of the ocean seafloor in the kind of detail that we need to understand a lot of the processes going on there. Certainly satellite imagery, can I click on it? Oops, it's coming about. That should be a rotating thing. Anyway, satellite imagery is using gravity. Thank you. Yeah, nope, sorry. Gravity to discover this was a global base of seamounts, and it should be spinning, but it's not. Anyway, there's thousands of underwater volcanoes. That's okay, no worries. Imaged, and even in 2014, there were discovery of many, many more using satellite data. So the interplay between satellite data and more traditional oceanographic methods has really transformed a lot of the ways that we get to see our planet and interact with it. There we go. There you go. So one of the things I wanted to mention is, even though we've seen thousands of these underwater volcanoes, many of them are staked out for mining now for precious metals. We've probably only been to a couple of these and looked at them in detail, probably less than 5 in the world. So they're hydrothermal breathing holes. They stay active. Some of them stay active for a very long time, and there's certainly important ecological implications for these volcanoes. And again, we've only been to a few of them and looked at them in detail. So there's really big opportunities for discoveries in these systems still. Going down to the next resolution, this is a detailed map at the centimeter resolution bathymetry map that was done by Mbari using their ROV Ventana. And so the image to the right there, you can see this is on the bottom right is a junction box. It's kind of like a small substation that we have cabled up on top of the volcano. And you can see now that we're getting to resolutions of centimeter resolutions and really being able to image the seafloor, which is critical to understanding how it evolves over time. Starting about 1950s, with the advent of nuclear bombs, there was a large increase in the interest in ocean bottom seismometers to detect nuclear explosions. Since then, there's been a large increase, although people would argue we need more of ocean bottom seismometers to image many things that go on the planet, both from the inner core out to tsunamis and storms. Some of them are buried, keeps the noise down, and some of them, more rarely, this is a short period seismometer that was drilled into a basalt flow, again, to keep it quiet, as a local observatory on one of the spreading centers to look at seismic activity along spreading centers. In addition, we have, through the cable array, the most active volcano off the coast of Washington and Oregon is called Axial Seamount. It erupted in 1988, 2011, 2015. And through the Ocean Observatories Initiative cable array, where we have a fiber optic cable running over 300 miles offshore, we were able to detect in real time the explosions. There was over 30,000 explosions. The seafloor fell about 7 feet, and there were over 8,000 earthquakes in a single day, marking the advent of the eruption, which ended in a over 400-foot thick lava flow and billions of microbes streaming out of the seafloor following that eruption. The other thing that's certainly noise in the ocean is of big interest, not only for looking at mammals and how their migrations change over time. And this is live, it was live, coming in off the cable of, there's a broadband hydrophone on the Oregon margin. And so with these cable observatories, the data are open to anybody in the world. And this is just some of the pinging is at ADCP on the mooring, but these are mammal whale calls that I can listen to for hours, right? But one of the things that's nice about the hydrophones as well as seismometers is that you can actually track the migration of whales and different mammals in the water column. And certainly there's a lot of interest in human noises and how that impacts the migration and mating behavior, because it interferes with the whales' ability to talk to each other. We've now been able to merge down and image actually get access to the subsurface. With the advent of the discovery of hydrothermal vents and chemosynthetic organisms, there still is a lot of interest of what the upper temperature limit of life is on the planet, and also how deep these organisms can live in the crustal environment and how long. And so through the ocean drilling program and now IODP, we have corked observatories where you can drill down into the sea floor, case the holes, and put a variety of instruments down into the hole. And they have packers that, so the ocean crust is the largest aquifer system, fractured aquifer system on the planet. And so there's a lot of interesting questions about hydrogeology in the biosphere and seismic events, how perturbations impact pore fluid pressures in the crust, and whether you can start making predictions on perturbations that may predate seismic events. And so there's the example to the left there is through a borehole observatory and looking at the perturbation and pressure response after the Tohoku earthquake. Similarly, they're moving on to now where you can put in those observatories, there's a way to sample the biosphere. So they have little capillary tubes that go down into the well holes, and you can measure, when you recover the fluids, you can analyze the DNA and look at the microbes that live in these environments. We certainly made a huge progress in imaging. I've always loved this image of 1934, which was from Beebe's descriptions of animals that he saw looking out of the sphere. In 1950s, started developing the first black and white cameras. My first job was developing 35 millimeter film at sea, which was horrendous, but on a rolling ship in the dark with chemicals. Around 1991, we started getting CCD cameras, and this is a hydrothermal vent on the Endeavour segment It's one of the most active hydrothermal systems in the world, and you can see this is a live mannequin for scale. Diving in the sub, it's always hard to get scales. From that, now we've moved on to, I like this contrast. On the cabled observatory, we have a digital or high definition camera that runs, it can run continuously. We keep the lights off. We're trying to figure out how it impacts animals and organisms there. But this is streaming live. Anybody in the world can have access to it. This is an active hydrothermal event, a little over 300 degrees. And every day, every 3 hours, this camera is going on and off. And then once a month, it goes for three days continuously. And there's many questions. So these are chemosynthetic organisms. If you looked inside of that mound there, it's actually massive sulfide, but it's completely covered in life that lives off of the gases streaming out of the volcanoes. The other thing that's going on, which to me is, I'm not a biologist, but I'm amazed at the way that we're able to image down at the micron levels now. And so one of the biggest questions now is at the micron scale of single-celled organisms or even viruses. We know almost nothing about them in the oceans, and yet they are the base of the food chain. The microbes are for the oceans. So they're getting these really high-end imaging systems with flow cytometers, and you can image things at the micron level now. And there's one off of Martha's Vineyard that's cabled. There's over 700 million images, and so they're developing catalogs of these organisms, and some of them are the specific images. You can now look for harmful algal blooms and let people know when they're happening. So there's a lot of societal reason to be doing this, as well as a lot of science to be advanced. One of the most successful programs for understanding the global ocean was the Argo Floats. It's an international program. There's over almost 4,000 floats now. Initially, they measured CTD and temperature, and those data were integrated into models understanding things like El Nino events. And now they're adding CTDs and going to deeper waters. Certainly, to compare to that, there's a lot more moorings in the water. They go at the air-sea interface for specific things, looking at how much CO2 is drawn into the water column. And they're developed, this is one on the right, is one that's developed solar-powered. So again, they're advancing the technology and the lifetime of these. They also use iridium connection, so we're starting to get near real-time data from the oceans from these. The last thing I want to talk about is the NSF OOI cabled array. So there's many tens of these arrays now in the world. Most of our telecommunications is coming from telecommunication fiber optic cables that span the sea floor with petabytes of data now. So in 2014, we finished the installation of the cabled array. There's over 140 instruments. It certainly is changing the way that we used to do science, where your data were yours, and that was kind of publish or perish. And now there's over 30 different types of instruments, all coming in at the speed of light on the array. The more advanced ones, we have moorings now that are also cabled that do water column experiments. They go up 9 times a day at 200 meters. This is off of Oregon, and what you see is probably the largest single array in the world now of many different kinds of instruments looking at the Oregon margin, which is one of the most productive areas in the world. It also includes surface expression moorings that are uncabled, cabled moorings, and gliders. This is an example of one of the moorings that goes up and down 9 times a day. And one of the things that I think is going to be really important is you can combine things like chlorophyll from the satellites that only image the very thinnest part of the surface to maybe 10 meters if you're lucky. And now what we're getting is full water column measurements from, in this case, 2,700 meters. So I think with co-registered, 18 different instruments that are co-registered in time and space. The last thing this is one of the best talks I've ever heard, is turning fiber optic cables, dark fiber optic cables, and using the entire cable as a sensor. So there's one of the most amazing talks I saw was this session on Monday where they used a Mars observatory to, it was down, so they used one of the fibers, they're 20 kilometers, and they can, by looking at the backscattering, perturbation and backscattering along the cable, they can image faults that were never seen before, microseisms, sea state dynamics, storms, things like that. So these are going to be coming online. There's thousands and thousands of kilometers of fiber optic cables on the sea floor now, and they're also starting to build smart cables. The first one is going in, I think, next year, where in the repeaters, they instrument the repeaters. So I think this is going to be a big change in the future of It's not quite the Internet of Things in the ocean, but it's certainly bringing the Internet into oceanography and sensing the ocean in brand new ways. And I think this is going to be an incredibly powerful system for imaging the ocean and making discoveries. So when we look at all the, certainly oceanography has been impacted and benefited from lots of other technologies. And I think with the advent of more power into the ocean and telecommunication cables, it'll be interesting to see where we are 100 years from now. Thank you.
Thank you. Right. I'm afraid we haven't got time for questions, but I'm sure you can talk with Deborah afterwards. So now we're going to move on. Laura Thompson is going to tell us about the glacier change.
Okay, sure. Thank you very much. So before I kind of dive into some changes, technological changes that have helped us advance our understanding of glaciers, I thought it would be, oh, sorry, wrong computer. Here we go. I thought it would be helpful to kind of review some of the questions that we as glaciologists ask. And primarily this includes understanding where glaciers are and how many there are. How are they changing, ranging from length, area, mass and volume changes? And what causes these changes? Things like mass losses and gains, energy balance, dynamic behavior, and feedback processes within glaciers themselves. And then we ask ourselves, what does the future hold based on kind of what we've learned? So based on these questions, we've also seen several key developments that have stretched across the geosciences. This has been going from analog to digital instrumentation, going from in situ measurements to airborne measurements to spaceborne measurements, and this has really impacted the scales that we can ask questions at, and then of course also advances in computing. So while I don't think I can spend 10 minutes to cover all of glaciology, Jane was very generous and instead allowed me to kind of focus on how we've seen how these technological changes have impacted the work that we're doing here at the Mcgill Arctic Research Station. So the Mcgill Arctic Research Station was founded, it will be 60 years ago next year, and it is located on Axel Heiberg Island. It's in the Canadian High Arctic. It's approximately 80 degrees north, and the island is roughly the size of Switzerland. And interestingly, a lot of the early researchers who worked there were Swiss collaborators with Canadians. So I think they felt quite at home. They even named some mountains, the Little Matterhorn or the Swiss Range. And essentially this camp was established. It was set up by this gentleman, Dr. Fritz Müller, a Swiss glaciologist. He was a professor at Mcgill University in Canada, and when he kind of wrapped up his work there, he moved back to work at ETH. And as part of being in the geography department at Mcgill, Mcgill was very interested in starting these research stations that span from Barbados all the way to the high Arctic. And so they were looking at climatological changes and all sorts of physical geography observations at a range of latitudes. But specifically for this expedition, their main scientific aim was to study the evolution of mountains and the strongly glaciarized and glaciated areas of western Axel Heiberg Island. So this is based on some of the early reports that we have from 1961 when this station was founded. Another nice thing was that they were really trying to do a comprehensive study in this region. So even though the primary researchers were glaciologists, they understood that it was an Earth system. And so they were not only looking at glaciology, but regional geophysics, meteorology, geology, permafrost studies, geomorphology, botany, even some zoology. And so this really provided a comprehensive study of that environment. So based on this, I'm going to go through a couple individual case studies of how we've seen technological advances in the way that we do our research at this station. So to do this kind of work, one of the first things that they needed to know was what was the regional climate in the area. And of course, this varies from ocean and a very coastal area up into the alpine. So one of the first seminal studies was conducted by Dr. Atsumu Omura, who some of you may be familiar with. He's really been a kind of icon in energy balance studies. And so he was conducting his PhD here. And there was a network of these climate stations that he established over his PhD. And every day for 6 days, he would hike to a different region in the valley to take manual measurements from thermometers, anemometers, their hygrometers, but these were all analog sensors. So in some cases, they were able to record data on kind of wind-up scrolls, but in other cases, you could only get data if an observer was there to read the instrument. Today, we are using automatic weather stations, but we've really tried to actually mimic the coverage that Dr. Omura had in his study. Now these are digital systems, all the data is logged, and they're able to run continuously. So previously, data was only able to be collected while Dr. Omura was in the field, which was at most from April to August, because it's quite miserable the rest of the year. And so now we go and we are able to program these systems to collect measurements every 5 minutes. Internally, it's able to do some calculations for us, so to bring together hourly and daily means. And we also get quality control, so we know if there's been issues with our instrumentation while we've been away, which is really valuable. And what we're doing this coming spring is we're going to be updating all of these stations with antennas so that we can actually download this data in the south. And it will also help us as we prepare for field work to know if any of these stations have issues. So that is kind of understanding the regional climate. When we get into the glaciology, one of the first studies that needed to be done was to actually know where the glaciers are, how many there are, and what are their characteristics. So this was actually Canada's first pilot study into glacier inventory. It was conducted by Dr. Simon O'Mahony, who was a PhD student at this time. And Simon used air photos over the island collected by the Royal Canadian Air Force. And he was manually outlining individual glaciers and assigning 18 different attributes to them, all based on image interpretation. So this is where the individual really needed to be an expert at interpreting air photos. Today, we can now manually classify where glaciers are using an algorithm using remote sensing. So this remote sensing has really been key to our global understanding of glacier inventory or gathering global glacier inventories. And actually, we just achieved in just the last 10 years a full global inventory of glaciers, and this is the Randolph Glacier inventory. Today, our accuracies in our inventories are based on the resolution of the imagery that we're using, as well as there are still issues exist relating to cloud cover and snow cover and debris cover, but it's really revolutionized the scale at which we can do glaciological studies. So when we tried to compare our modern inventories with Dr. O'Mahony's inventories, this is where we start to run into some challenges of comparing historic data with contemporary, because Dr. O'Mahony's work was pre-GIS. So we didn't have vectors of glacier outlines, we just had points. So we had to get a little bit creative with how to compare point data with vector data, but we were able to kind of isolate things to basins to see where we have glacier losses and gains. On more of a local scale for the glaciers that they were studying at the site, early maps were a really important tool that they needed to create to set a context for their work. So early surveying was conducted by theodolite and altimeters, So in situ surveying, and then also air photos were an important part of this, and manual photogrammetry using stereo plotters. So I don't know if anyone's ever seen old stereo plotter, but they're enormous tools that are essentially used to very precisely change the distance between two stereo photos to measure the parallax between high elevation and low elevation sites. And through this, you can start to build a 3D model. They made some really impressive maps, actually some of the most beautiful alpine maps that we have in Canada, partly likely due to the fact that they were Swiss cartographers making them. But they reported vertical accuracies of these maps of plus or minus 10 meters, which is actually very good for a region that spans almost 2 kilometers in elevation. And essentially, they had to bring their elevation up through triangulation from sea level, correcting for tides. But what's really impressive is that when we actually go back to the ground control points that they use, these kind of cairns that we sometimes come across when we're hiking, when we put our differential GPSs on them that have 2.5 centimeter accuracy, we actually find that their ground control points were within plus or minus 1 meter. So I think they were being very conservative with their map accuracies. We are continuing to do kind of more detailed mapping of our glaciers of interest in the region. We are continuing to use air photo surveys, but now our camera systems have much higher resolution. We are able to fly at lower elevations. We're able to sync our cameras with GNSS, so we have very precise camera locations. And from this, we can use a tool called Structure for Motion to make very high resolution 3D surface models. So here is one that was put together by my student Jeremiah Lee just over the terminus of White Glacier. And it's really incredible. We are able to discern small surface streams that are maybe just a few centimeters wide. And you can actually zoom in and kind of put yourself right back at your field site. So it's been a really helpful tool for us in many ways. And these have kind of plus or minus 5 centimeter resolution, so we can actually start to look at annual volume changes. And Jeremiah will be using this work to map glacier structures and to see how those have changed over the past 60 years. Updating these models has allowed us to look at glacier-wide volume changes. So this is where the historic maps plus our modern maps, bringing those together has been incredibly valuable. We've also been able to update the hypsometry of the glaciers that we study. So this means updating the area elevation distribution. And this has allowed us to improve our mass balance estimates as the geometry of the glacier changes. So we've been able to calibrate our long-term record to correct for these surface elevation changes. So it's improving kind of our broader glaciological work as well. If we look a little bit at process understanding, one of the seminal works to come out of Axel Heiberg Island was by Dr. Fritz Müller. In his very first year there, they were skiing up into the accumulation of White Glacier, and they were finding these huge slush avalanche, which is actually really dangerous, a dangerous place to be working. But understanding these different zones, or what we call facies, in the high elevations of glaciers is important because we're essentially looking at how much meltwater can be retained within the high elevation snowpack. And the more that can be retained, the less is being run off and contributing to something like sea level rise. So this is why we care about these kind of different zones, whether it's just a percolation zone or a saturation zone or an slush avalanche zone. So Fritz Müller was very central in kind of building up this understanding, building on the work of Benson in 1959. So as we're seeing increased melt at higher elevations in recent decades, we're revisiting this idea of the glacier facies and trying to look at how these zones are changing spatially through time. Today, instead of skiing, which is a lovely way to do field work, but instead of skiing and doing snow pit measurements, we tow a 500 megahertz radar system behind our snowmobiles, and essentially the radar system is sensitive to the distinction between ice and what we call firn, or not quite yet snow. And so we're able to map the amount of ice, or the volumetric ice content, using our radar system. So we can start to classify these zones, again, using thresholds of radar backscatter. And so my student Dana has been essentially running these surveys over the past 2 years, but we have records going back now 7 years. So we're able to look at how these different zones change spatially, and this is going to also improve our mass balance estimates by allowing us to estimate how much high elevation melt is being trapped within these glaciers and how much is running off and contributing to sea level rise, and how kind of this will change over time, so it also supports our projections. One last study that I'll quickly note is that by Dr. Elmet Eken. She had the onerous task of waking up every 4 hours and using a manual theodolite to measure a network of stakes on White Glacier. And it was previously thought, or it was thought at the time, that cold polar glaciers did not exhibit these speed-up events. But her work showed that that in fact happened. So we're repeating her work, and I always feel a bit guilty when our robotic theodolite wakes up and repeats these types of measurements, but we can repeat this work using GPS and theodolites. And what we've been able to see is that the glacier is slowing down at lower elevations, but in fact speeding up, which was a surprise to us. And we think this is due to high elevation melt and meltwater being able to make it to the base of the glacier. I'll skip that part and just say that in doing this work, what I've really learned is that this historic data has really been incredibly valuable to helping motivate and steer our current research today. And it really falls within the theme this year at AGU, which is celebrating the past and inspiring the future. We could not do this work without the historic studies that were done. There are challenges relating to changes in data structure, going from analog to digital systems. There's a lot of data entry for undergrads, but they don't seem to mind too much. And also the spatial scales and temporal resolutions at which we gather our data is changing. But overall, this work has really taught me to think about not only how we can make the most of the work from the past, but how can we also design our data today, and how can we conduct our research today to know that it will be useful and inspiring for future generations to come. So, thank you very much.
Thank you. I'm afraid we haven't got questions, but I'm sure Laura will answer them at the end. So now we're going to move on and look at a century of water data.
Hey, what's going on, everybody? How you doing? I'm Bronco. I'm an associate professor at the University of Michigan. I'm actually really excited about this session because, oops, let me back up here. Am I going back one slide? Which one am I controlling right here? Okay, cool. So I was really excited because usually I just plow ahead and just do my work. And when I got the invite, I was like, Jane, so am I supposed to talk about a history of water or just my project? She's like, history. And it's like, whoa, I figured a professor is supposed to be able to do that, right? So it's like a kind of it made me go back and think about like who are my heroes and what's kind of interesting stuff. Because it turns out people have been shoving widgets into water for quite some time to learn things. So because it's the informatics session, I think just to kind of review like why water is important. I know a lot of us are in different fields. It turns out, you know, we use it to grow our crops. We drink it. And as this awesome image shows, we also use it for all sorts of new ways of transportation and recreation. So it's quite important. And obviously, you know, with all the good comes some bad. And as a lot of us know, a lot of our ecosystems are sort of like being really stressed by things like algal blooms and pollutions. And it turns out, as this other image shows, floods hurt people, okay? This one's a little bit comical, but like actually floods are really, really dangerous, okay? And so people have known this for quite some time. And so it turns out you can look back like 3,000 years and people have tried to find ways to quantify water. So this is an image of in northern Africa and what's now Libya, some of the first instances of water management using some sort of quantity. So what you see here is a water manager would toss some straw into it seems like these slides are auto-advancing. Basically would toss a straw into this canal and start this water clock. So this bowl would fill up with water, and when it fills up, they toss in another piece of straw, and that's basically how much time you have to remove water for the fields. And so this was actually quite a good way to measure water systems. And so, that translated obviously to the ancient Egyptians, and some of the sort of early ways to measure water were just basically lines in the wall, right? So what you do is whenever there's a flood, you mark it, and when there's another flood, you mark it, and you put these near big river systems, and essentially you use these marks to try to figure out like how the crops are going to look like this year, or how many things are going to get destroyed. But basically people figured out very quickly that water is a deep experience, we need to kind of track it. And so they built pretty massive temples towards it. This is one in the Nile River that I think would make any USGS gauge. People deploy them look like this, pretty envious, right? Like, this is amazing. It's like a massive structure whose sole purpose is to basically just measure the level of water on the Nile River. And you can go visit it. It looks like kind of some sort of religious structure. It's pretty sweet. So essentially, moving ahead, those kind of notions of measuring water by drawing lines on buildings and other things have existed for quite some time. And you can see some here. The left one is in the Czech Republic. There's some really famous ones that obviously been updated with new numbers, but they've been in river systems for quite some time, right? This idea of measuring water level and tying it to day-to-day things that we care about as a society has been around for quite some time. Now, obviously, scientists and other people are not just content with knowing what the water level is. They want to know how fast it's moving. And so if you look back, like people like Da Vinci, which is actually shown right here, we're kind of figuring this out. They were saying, like, well, if I tie a string to a little bob and throw it in the river, the more it pulls on it, the faster the velocity is, and therefore we can kind of estimate the quantity of water, right? So, I know this is supposed to be about a century of water, but really this stuff has been going on for quite some time. And so this is an image of turn of the century, 20s in the Nile, of people basically sitting on a cable and measuring water from up above. I just really like this one because people are doing field work in suits. I just think that's really cool. But anyway, turns out actually in the United States, this kind of picked up also, actually before the turn of the century. So in the late 1800s, they figured out you can basically stand above a river and shove this propeller-like thing down there, and the faster it spins, the faster the velocity is, right? And some of them would have a cable attached to it that maybe would have a current or a voltage coming out of it based on that speed. And so basically what you would have to do is just build these things that hover you over a river, and you toss this thing down, and it measures water velocity. So this is actually an image of the first U.S. Geological Survey river gauging station in the United States, in the Rio Grande. You can see here 1889. So they've been doing this for quite some time. And what they basically figured out is if you measure water, it helps a lot of people who are trying to grow crops or prevent flooding or all these other things. And so that really kicked off almost a century of building water infrastructure specifically related to measurement in the United States. So they said, okay, this is quite useful. What we can do is basically correlate the velocity of this water to the level, and as long as we measure level, we can figure out how much flow there is. Okay, so it's just like a correlation. They went out and they surveyed, right? Because the USGS, that's what they did. They surveyed. And so this turned out quite positive, and they started sending people out, just a bunch of guys with beards basically, to go out and said, build America's water measurement infrastructure. So you can see them out there with their survey methods, and basically what they would do is just take these structures and at that time toss them on the back of horseback and take them out to these rivers and streams and measure it. And so they would build these things. You can still see the cable there, right? So this is one that was obviously built a little bit later once we had automobiles, but basically it's a concrete structure and you still see that little cable that somebody would suspend themselves in and hover back and forth. And obviously, like the manual way of doing that improved over time as well. So you started introducing a little bit more sort of automation. So what you see here is sort of like an old school river gauge that it has a little bob attached to a string, and that pulls on basically a needle, right? And you have like a little paper spool spinning around, and as the water levels change, you draw those down on paper. This is still used in a bunch of places, believe it or not, just because there's some lawyers out there who argue that, well, your ADC, how do you know in that millisecond between reading number 1 and reading number 2 something didn't actually happen? So some people say, just draw it down on paper, okay? But basically, they've been doing this stuff for quite some time, and that formed the basis of a modern kind of infrastructure for measuring water in the United States. This is a picture from the 50s of them just continuing to build these gauges. And you might say, like, whoa, Bronco, is that an Instagram feed? Absolutely, because if you go to the USGS, they have a USGS stream gauge Instagram feed that is just awesome. My students and I read it all the time. It's historical photos, it's new photos, it's them sort of pushing the frontier, but they have a really cool social media presence, and I just want to kind of advertise it because I think it's really cool. So anyway, moving ahead with that, what happened was you sort of replaced that needle that draws pictures on paper with obviously, some sort of more automated instrumentation, which was replaced over time with maybe pressure transducers or these kind of bubbler systems. And the thing that really made it work was connectivity, right? So you start logging the data locally, but now you can send it out. And the thing that really kind of made that possible was long-range wireless, and then obviously, like when satellites got introduced, the ability to relay water levels in real time, which sort of started building the foundation for America's kind of new water infrastructure. So you still see these huts, these sort of small structures that are built near rivers and streams, and then, again, their purpose is to measure water level. So what you still have to do is you still have to do the thing, you're not suspending people above cables anymore, but they're still going into the water and putting, surveying equipment and these little propellers in there to measure the velocity of that water. Because once you get that velocity of the water, you can estimate the flow, again, from the level. And so what that gave us is basically a new way of doing this. Now, obviously, things have scaled down, because as most of you know, like microelectronics have become more advanced, and so now you might not need these huts anymore. Now what you have is more advanced systems that fit in a more compact form factor that can be suspended possibly over bridges, and sometimes it doesn't just measure water level. So this looks like to me like either a radar sensor that measures water level, or it could be an ultrasonic transducer, which is a slightly cheaper way of doing it. But more modern methods are being pitched right now that basically say, look, we can measure velocity and level at the same time using radar methods. So your radar sensor gives you the depth of the water, right, the distance of the water, but also through the Doppler effect, it gives you velocity. And as this little connectivity diagram here shows, it sends it to the internet, and you can get it in real time. And that's not to say that people aren't exploring different methods. So this is a company that I saw that's actually based in research, obviously, that uses cameras, right? So they say we have lots of cameras out there, and this idea of drawing lines on buildings for millennia is still useful, because if we put like a visual gauge in the field of view of a camera, we can still estimate water levels. And so there's a lot of products being pitched out there now that basically say we can do this using cameras. There's a really exciting kind of test bed that's being deployed by the U.S. Geological Survey in Delaware right now. That's sort of the next generation of this. So what they basically said is we're going to sort of beef this up. We're going to do new things, and we're going to deploy this really densely in a watershed. And they're evaluating all these new technologies there. So along with the sort of older way of doing this, they have these like next generation stream gauges. And I would encourage you, if you ever have time, to go on this, because it's pretty cool. It's kind of showing like what's next for the USGS. Obviously, water is not just something you measure on the ground. We've discovered over time that it's also useful to measure it up in the sky. And that's not really I know there's people who are more qualified to talk about this here, but essentially what happened in the 40s, the Navy basically said, hey, we got a lot of these leftover radars, and they seem to be picking up clouds. They talked to the National Weather Service, and we're like, you guys want them? And they were like, sure. So they gave them, like, I think, a bunch of radars, and that formed the foundation of what basically has become the next rad system in the United States. It's our sort of real-time view of the sky, of how the clouds are coming in, and how that might manifest in terms of like precipitation, which ultimately, I guess, turns into water flow. And it's not just radars, but they also maintain a very large infrastructure in terms of rain gauges. And that's also been appended to, obviously, through massive innovations in terms of remote sensing, which, again, like other people are going to speak to this, but I just wanted to show some of the early sort of weather satellites and how they're evolving over time. This is an image that was basically put out. They're basically coming out with many new ways to measure water from space, and specifically weather, which is obviously really, really useful in terms of water management. And I wanted to just back up really quickly to discuss the terrestrial system, because that's kind of what I work on, right? So weather is really, really important, but we still have some stuff that we're working on the ground. So here's your USGS gauge, and I just wanted to show this image right here of the present-day American water information system. So what the United States Geological Survey has done, they've deployed something around 8,500 stream gauges in the United States. So that's 8,500, and that's a continental scale system. A lot of us work on field sites, and we know how much work it takes to deploy sensors. Imagine maintaining a national scale water information system. Like, that just deserves a tremendous amount of credit, and it takes 100 years to do. So that's 8,500 gauges, and I think I'm just really impressed by that. I just like what motivates me. How many counties are there in the United States? Do you guys know? 8,500 gauges for how many counties? 300? Another number? 1,000, another number? It's about 3,000, okay? So when you do the math, that's about, again, depending on where you are on the coast, we have more of these gauges, but it's anywhere between 0 to 3 gauges per county. So we do the math of the land area of the United States. Even though this is quite impressive, if you zoom into a place like Michigan, which is where I work, you see a lot of counties that don't have any water data. They're still investing millions of dollars into their stormwater infrastructure and other management practices, but basically what it boils down to is 1 gauge per 500 square miles. And to give you some sense for like what 500 square miles looks like, San Francisco is 50 square miles. Obviously, you know, it's more population density, that's not the point, but in terms of land area, both San Francisco and New York aren't as big as like the average of how many gauges there are in the United States. So why I bring that up is because water is experienced very locally, okay? Your neighborhood floods, okay? Your Pizza Hut floods, and we don't know what's going to happen basically at those kind of resolutions, right? The image that I kind of like to show is Detroit. We had in 2014 $1.5 billion like basically flood in Detroit. It was a really massive event, and the images I'm showing are basically in areas where people just took photos of just flooding the devastated neighborhoods. And none of those are near big sort of floodplains. They're not near big rivers. They're not near sort of places where you would have these instrumentations. So basically, a lot of places where people experience day-to-day things with water, like flooding, are completely unmeasured. And so there's basically an opportunity to sort of keep growing into it. And so what we've been working on in lab is sort of like cheap technologies to allow you to do this at scale. So instead of saying like, okay, USGS is really sophisticated, they build awesome stuff, we like what they're doing, let's sort of supplement that with cheaper wireless technologies that are on the order of like $500 that you can put out and really sort of blanket water systems. So this is pictures of the students out in the field measuring things like water level and really putting these small devices out there to start giving you data in places where it's really difficult to get data using more sophisticated approaches, right? And so what we've done with this is an example of a network we built last summer. It's 50 sensors across about 500 square miles, okay? So like going from 1 to 2 to 3 to 50, and because we feel like that truly enables kind of next-gen kind of decision-making in terms of water systems. All the stuff is connected to the internet, and the data basically feeds back and allows you to see things at the kind of resolutions that really weren't possible to be sort of measured before. And so, gotcha. So this shows the network that we've built over the last few years in the state of Michigan, just by a bunch of students actually, okay? Putting out sensors, kind of measuring water systems, and it's enabled all sorts of new applications, starting from sort of new science that shows you like what is happening at high resolutions in urban water systems, right? You might have 1 or 2 USGS gauges, but now we can see what's happening in each neighborhood. And it's enabling all sorts of like things that we weren't expecting. A lot of like decision makers are using it for local emergency response, for lake management, for reservoir management. So these are scientific instruments that we put out there that basically are allowing all sorts of new applications, in this case like real-time control of water systems that really would have been really difficult to do if you didn't have high-resolution data. And so lots of municipalities want this kind of stuff, but they can't build it. So this is not one of our projects. This is in Texas where they have lots of, they have like 100 gauges out. But the fact is that most municipalities can't pull this off. So if the USGS is not going to do it, most municipalities are struggling maintaining basic water systems. Like the idea of like just escaping a ransomware attack on your 911 system. You know, they don't have time to go out and deploy lots of sensors. So what I want to leave it with is, despite of the fact that we're talking about building smart water systems and all these things, our ability to measure water systems is far exceeded by the ability to process the data. So what I'm getting at is we don't have enough data, and I'm not sure if the federal government is going to multiply the number of gauges by 10. In fact, it's going down right now. So who's going to fill that gap? I think it's going to be a combo of basically, scientists trying to do the work on the ground and maybe new companies, right? Because right now we have one game in town that measures water systems in the United States, and I think some level of diversity wouldn't be too bad. And so I just want to give credit to the students who worked on it. Thanks.
Thank you. Right, and now we're going to move on to looking at atmospheric sensing from space.
I should stay here. I'm very happy to be part of the session. I think it's great. We're looking at the history of these measurements and pay homage to the people that came before us for some really exciting work, and maybe look to the future. So I'm going to try to do all of those things in my talk. I should point out I have underachieved a little bit. I'm only going back 50 plus years, not 100 years, but I hope that's close enough. PC, yeah. I hope I don't have to be Mike Little. You did a much better job than I could ever do without slides. You think so? Excellent, okay, thank you. So I'm going to be talking about microwave atmospheric sensing from space, and I will acknowledge some contributors to this talk. I'll mention these folks as I go along. So let me first give you a little context on why microwave measurements are so valuable for Earth observation, weather and climate. So the microwaves are able most of the time to penetrate the clouds. So we can see what's going on underneath the tops of storms, severe weather, dynamic things that we're trying to track. They're sensitive to temperature, moisture, and a lot of trace gases that are interesting for process studies. And we can actually use polarization information to say things about clouds and the surface for more detailed studies. It's a critical driver for the forecast and for climate studies. We use microwaves for all kinds of time scales and spatial scales. So very important stuff. So to pick one seminal point in the history of this, I chose this. So Dave Stalen may be a name that some of you are familiar with who follow this area. So he wrote a paper back in 1966 pointing out that we should be able to use microwaves to measure liquid water content for clouds, and pointed out how well he think that we could do that. That was 1966, and that was based on some terrestrial measurements of atmospheric attenuation. So this set off, a line of research on, how can we build instrumentation to do this, fly on aircraft, fly on spacecraft, and make these measurements on a global synoptic scale. Can we do this, and how well can we do that? So this is one of the first mentions of this. So here's kind of a timeline of what I'll call synoptic microwave sensing. These are cross-track scanning instruments spanning 40, 50, 60 years. And there are really three eras here that I want to point out. And can I do this to point? Sure. All right, so in the early 70s, this was this push to try to build instrumentation to prove out the concepts in this paper. So there's a sensor called Nihms, which was a microwave scanner that flew on the Nihms Satellite in the early 70s. A more sophisticated, had more channels, more spectral resolution, better spatial resolution sensor called SCAMS that flew in the mid to late 70s. And the culmination of this first era here is something called the microwave sounding unit, which was used operationally to provide measurements for forecasting and for climate. So that's really the first era, is this culmination in MSU. And then we moved into what you might think of as a second era, where there's an operational phase of these measurements, where NOAA used the Advanced Microwave Sounding Unit and ATMS to really drive the forecast. So today's forecast is heavily dependent on microwave measurements. This is really the principal source of information for the forecast. So this is the kind of the second era. And I think it's a really exciting time now, because we're entering a third era, where we're starting to use things like microsatellites and constellations and some of the information technologies that Mike Little talked about to thread these systems together into networks. And that's really exciting. So I'll talk about those at the end of the talk. But let me take you a little through the history of the timeline here and point out, so these are all cross-track scanning instruments. They scan across the satellite track and build a global image. There are other geometries that we can use. I'll point that out as well. Okay. So here is some data taken from the Nihms satellite back in 1973. And they were able to prove a lot of critical process information with these measurements. So this is somewhat of a busy chart, so let me walk you through this. So there's water vapor shown here, there's brightness temperature, and there's liquid water, all measured as the satellite flies across this storm, right? This very nice cyclonic structure here with a clear eye. So the point here in the middle is just warm core. So for the first time, they were able to show that there was a warming inside of the core that they can measure with a microwave radiometer. And that warming turns out to be highly correlated with the intensity of the storm. And I'll come back to this later in the talk. So there's this vertical warming. The sensors had sufficient spatial resolution to capture this. So we're talking about on the order of 100-kilometer spatial resolution back then to measure this. So you can see the water vapor with the clearing of this eye is captured very nicely with this instrument, and also the liquid water in the cloud. So all of these things were proven out by this Nihms sensor back in the early 70s. So this was a lot of proof of concept by the Nihms satellite. So moving off that, so here's a picture that I like to show occasionally. So here's the science team for the SCAMS instrument. And I don't know if maybe some of you recognize some of these guys. I think, let's see here, Joel Susskind is right here. I saw him earlier this week here. Oh, there he is. Okay, awesome. So maybe Joel can tell us who some of these guys are. Phil Rosenkrantz is over here. Dave Stalin is there. We've got Tom Wilhite, Bill Smith, and so forth. So these are the heavy hitters, right? So when I first came onto the scene in the late 90s, I was reading all the papers by these guys and still do. And another fun fact about this room is this is where I had my doctoral oral qualifying exam. So seeing this picture kind of brings back, flashbacks of, stress. But anyway, so these are really the guys who push this field forward. And here is a picture from the SCAMS sensor. So now we're moving into the late 70s, where we're seeing global pictures now of water vapor and color liquid, and these are teased out from using the multispectral attributes of the sensing channels, right? So we can get these global images now of the water vapor, and you can see how this is. Now we can use this data to start to forecast the weather and trend the climate, and we have this over long time scales. We can do decadal type records. So there are other ways to get these measurements. So I've been talking about cross-track scanning. Here's a picture of the ATMS instrument that now flies on the current generation NOAA operational enterprise. But there are other geometries. So there are conical scanning instruments. Tom Wilhite in the previous picture was really a pioneer there. We keep the incidence angle fixed as the satellite scans, and that keeps the resolution constant over the scan and the polarization constant. So that's useful when you're trying to do imaging. And also limb scanning is a very valuable way to do this, where we scan the beam out from the satellite and look at the limb of the Earth. And increasing the path length, we can start to measure trace gases and you get very high vertical resolution with that type of approach. So these are really the three ways that we use microwave sensors to get these data. All right, so here is a global picture of a 30-year time trend from MSU. So the microwave instruments are very valuable for these multi-decadal climate trends because the biases from the clouds are minimal with the microwave sensors. So there's this, going on, 40 years of climate records that stitch together all the sensors that have flown the MSUs and the AMSUs, and more recently ATMS. So these are very valuable climate records that we get from microwave sensors. There are other very useful products. So here's an example of a precipitation climatology derived from the AMSU, showing total rainfall. This was done back in 2010, but there's studies over the entire globe of how is the climatology different with respect to the regions of the globe and so forth, stratiform rain versus snow and convective rain and so forth. So we can tease out all these things with useful uncertainty with passive microwave measurements like this. Okay, so I mentioned the warm core anomaly that we can measure. So with sensors like AMSU, where the technology over the course of the decades, what has happened is the spatial resolution of the sensors has gotten better. So with AMSU, we've moved from the 200 to 100 kilometer class spatial resolution to now 50 kilometer resolution with AMSU. And that's good enough where we can do some very detailed studies of hurricane intensity. So we can look at the wind structure, look at potential instabilities, having to do with how the tropical cyclone is moving dynamically and tracking some of the features. And you can see very clearly here the warm core anomaly, which can be related to intensity. So there's a whole body of work going on now on these types of techniques. And as the resolution of these sensors improves, these techniques really get better because we need a lot of, to capture dynamic behavior both in space and time to measure these types of things. All right, so in terms of the microwave limb sounding, here's a slide from Nathaniel Ives from JPL. And really the key here is we're trying to measure the trace gases. So the US has flown something called the microwave limb sounder, and there's been 2 incarnations of this over the last few decades. And the Europeans have flown some sensors as well. And the idea here is to look at things like ozone. So back in the early 90s, there's a very famous paper that tracked the ozone hole over the South Pole and the North Pole, and they were able to say some things about how the Arctic compares to the Antarctic, and there were some surprises in terms of how the ozone hole was developing and intensifying and things like that. So that's a lot of really nice work on ozone came out of the MLS and continues. Here's a chart at the bottom. They call this the tape recorder chart, showing the stratospheric circulation, the drying and the moistening of the air back and forth over the course of many years. And the tape recorder, I mean, that may be kind of a dated way. I don't know if a lot of you probably will understand that, but this is this helical behavior of the spatial distribution of the circulation is kind of interesting. And in the upper right here, now moving a little bit to, how will we improve the measurements going forward? So here is a typical radiometer from MLS. It's about 40 centimeters long. It has 25 channels. Now today, they're trying to make a system with 4,000 channels, right, on a single chip, right? So there's this tremendous amount of work going on in miniaturization of the sensors, integrating a lot of functionality on a single chip. Here's an example of that. And what this gives you is better spectral resolution and improves, the final product. So there's a trend going on now of miniaturization, smaller, more affordable instruments. Here's one example of the technology enabling that. Okay, another big thing now are CubeSats and microsats, where we can exploit that miniaturization, fly smaller satellites, fly more of them or fly them more often, and make measurements that we, in many cases, couldn't make before. Here's one example. This is IceCube. So Dong Wu at Goddard is the PI on this, and this is the first time that they made measurements near 883 gigahertz, which is tremendously important for characterizing clouds. So this is a fairly simple satellite that spins around and directs the beam across the Earth with 12-kilometer resolution. And when you do this, you can derive a lot of very useful features having to do with cloud ice. So here is, I think this is the first global image of cloud ice at this frequency. So this was enabled by this CubeSat technology where we could fly the sensor fairly quickly. And these measurements are very valuable because there are the regions of the spectrum where we haven't measured yet. So we can make measurements in the microwave that I've showed before and in the infrared. But the submillimeter kind of bridges the gap between those two spectral measurements. And this is a very important quantity because this is one of the largest sources of uncertainty for climate study. So they're able to fill in this gap here with these kinds of measurements. This is, I'm showing you a water path as the PDF of the water path. Okay, and another interesting development is the commercialization of observations of the Earth, and microwave is no exception. So there's a company, Orbital Microsystems. Mike Horowitz gave me this slide. So they recently launched a CubeSat from the ISS, and it's providing some very nice data. This is an example of a tropical storm overflight. So this is another area where the way that we get data and the way that we use data is starting to change, right? So we have these commercial companies that would like to provide data that we use for these studies. Thank you. And I'll close out with a slide. So another approach, of course, is to proliferate the number of measurements that we can make, fly a lot of them. So this Tropics mission that I'm affiliated with, this is the NASA Earth Venture Program, and the idea is to fly a lot of these very small CubeSats. We're going to fly 6 of these 3U CubeSats in a constellation in a very specific orbital configuration, so we can overfly tropical cyclones with very high revisit rate, below an hour revisit, and that'll let us study the dynamics and measure the warm core and the tropical cyclone, the rain bands, the asymmetries, things that we can correlate to intensification of the storm. So we've built the hardware. Here's a nice kind of artsy picture of the CubeSats. We hope that we will launch this in the next couple of years. So we're waiting on NASA to find a launch for us. We're going to launch one of these hopefully next year as a Pathfinder mission, we hope. Okay, so with that I'll conclude. So I hope I've given you a flavor for where we've come from passive microwave observations. There are lots of valuable information we get for both the weather and the climate applications. The technology advancement is really rapidly improving these days, and we're looking forward to a lot of constellation-based microsatellite solutions to augment the way that we've typically done it in the past. With that, I'll stop. Thanks.
Right, thank you. And now we're going to move on to look at UASs.
All right, good morning, everyone. My name is Maciek Stachura. I am the CTO of Black Swift Technologies, And today I'm going to be talking with you guys about UAS or drones for Earth science. So I know the theme of the talk's 100 years. You know, UAS for Earth science aren't quite 100 years old. You know, most people would peg it at around 40 years with the NASA mini sniffer, which was a hydrogen-powered aircraft that was first developed in the 1970s and fueled and operated by some rather brave engineers, I would say. So my talk's going to go a little bit into the past, focus and kind of give context with the current state-of-the-art of drones for Earth science. But I really want to focus on sort of the emerging technologies and what I see as the future of drones for Earth science and where it's going to go, you know, through 2100. So just one slide on the past. You know, this, you know, up in the top right there, we have the Aerosonde, which NASA flew into a hurricane. You know, this was early in sort of the field, or, you know, this types of studies. These were, a lot of them were repurposed DoD systems. There was a lot of custom-built aircraft, which are, you know, time-consuming, expensive to put together, along with some inexpensive hobby-grade systems. But, you know, the main takeaway I want you to take from this slide is that early on, you know, the pioneers in this industry really had to, you know, wrestle these systems, get them to work. It took a lot of effort to do, even just to get one data set was just a great win. But what it really did is it showed the value of this in situ data collection from unmanned aircraft systems. So now if we fast forward to what I consider the current state of the art, this is a project that happened in the summer of 2018. And over a 6-day period, there was over 1,200 UAV flights conducted with Earth science sensors by, you know, 50 different aircraft teams in southern Colorado. And the reason this was possible was because we're starting to see, you know, really the use of commercial and consumer systems, which are much lower cost. They're reliable, they're easy to use. There's been a big contribution from open source hardware and open source software that really lowered the cost barrier of entry. And one of the neat parts of this project is we're starting to see the emergence now of unmanned aircraft systems platforms that are purpose-built for atmospheric or for Earth science in general. So another project I'll mention, or another mission that I think well captures the state of the art, is the Malibu. It's run out of NASA Goddard. At Black Swift, we developed the aircraft and the sensor package for them. And it's really, they're looking at calibration of Landsat. And the way that's done now is that there's towers and sensor networks on the ground, and those are used to calibrate satellites. But that's, if there's any data scientists in the room, you know that that's a really big gap in scales that you're trying to bridge for calibration. So the neat part here to me, and the main takeaway, is that we weren't trying to force unmanned aircraft to do Earth science. It's Earth science looked at their requirements, and an unmanned aircraft is what satisfied it. And that's still an ongoing project. And sort of the last one, and I would peg this into probably at the highest of the state-of-the-art category, is a project that just happened this past August. And this is now a purpose-built aircraft that was designed to fly into volcanic plumes, operate under very difficult conditions, and carry a very large set of sensors. So this one, I think, had 12 different sensors on board. It had multiple trace gas sensors, particle counters. It had a thermal camera. You can see a thermal image there that's one of the eruption areas in Kilauea. But the exciting thing to me here is that now we're looking at purpose-built platforms that are designed to really do the science and enable better science. Okay, so I'll just kind of skip through this one a little quicker. We're going to look at some emerging technologies, which I think are some of the key technologies for, you know, the next 10, 20, up to 50 years of unmanned aircraft. And, you know, the first big one is big data, and that's coming from a much wider industry, and that's really allowing us to have value and show us the importance of collecting more and more data and getting useful scientific results out of it. The one that I'm most excited about is autonomy. So when I first started with unmanned aircraft systems, you know, we considered autonomy, we manually launch a plane, we get it up flying, we hit the switch to go to auto, we cross our fingers, and it flies some waypoints. And that was autonomy to us. From the next step after that was we started looking at fully autonomous flights. And now we're starting to see the advent of a more sophisticated flight planning that's more mission-based. So here I have an image that shows this is what the FAA envisions as the UTM, or the unmanned traffic management. They want you to fill and satisfy all these little bubbles to be able to operate an aircraft fully autonomously in the airspace, which I think is real important for Earth science. Now, as a UAV designer, for you scientists, I want this to kind of be condensed to one bubble, and this is all you would see, and it's, aircraft, go do my science. The aircraft would tell you yes, and go do it. Now, to do that, it's going to require, automated pre-flight checks, fault tolerance. We really need to improve some of the autonomous aspects, and we are, so it's exciting. So there's really sort of two key technologies that are enabling this increase in autonomy. So this first, and they're both machine learning based. This first example I have here is using machine vision. Right now for manned aircraft, flying over an area, it has a lot of advantages. If its GPS isn't working, the human can navigate. If its engine fails, the pilot is trained to set it down somewhere that's not a runway. And machine vision and machine learning have given us the capability to start automating that and putting that on unmanned aircraft. The three images I have there on the bottom are just an example of images we've collected. So on the left, that's just left is a raw image. This is what the small camera on the aircraft sees. The next one is running a process called semantic segmentation. So what that's doing is classifying every part of that image into things like low vegetation, water, people, cars. And then finally on the right is it now takes these classifications, puts kind of safety buffers around people, cars, and it's telling you where you can and can't land in the event of a failure. Now the neat part is this is using on the order of $300 hardware that weighs 100 grams, and this happens this entire process runs at one image per second, so it's extremely fast. It's something you can run the entire time you're flying, and I think it's going to be a big step for safety. It's going to be able to do things like navigate its way home without GPS if there's any sort of jamming. It's going to be able to land away from people, things like that, which are big requirements coming down from the FAA. The other big one is intelligent onboard diagnostics. Now, I don't know if there's any Earth scientists in the room who have used unmanned aircraft, but that top right plot shows that you've entrusted your very expensive, very hard designed instruments to something that's failing at, per 100,000 flight hours, it's failing at, over 4 or close to 4%. Now, if we compare that, you could say that, hey, unmanned aircraft are a new technology, that's not so bad, but, personal GA there is at 11.9, and that is general aviation, and that is the worst of all the aviations. And now if we go to the worst year of general aviation when it was a new technology, which is in 1938, its failure rate was still 20 times better than current unmanned aircraft. So we need to do better than that, and we are, but better hardware, better technologies, but in the end, to get that rather large number down, it's going to take much more advanced capabilities. So we've kind of grouped that into two areas. So on the left, we have or on the right, sorry, we have, or my right, aircraft need to be able to track themselves long term. So we've been developing tools, software, and algorithms that monitor your onboard currents, monitor your onboard vibrations, and warn you if things need to be replaced or need to be fixed before it happens. Now, and that's great, and I think that's going to reduce the accident rate significantly, but you're always going to still have problems that happen in real time. So on the right there, it was a flight we conducted that lasted only around 20 minutes, and we saw a real decrease in performance, and we landed quickly. You can see how much ice built up on that wing in 20 minutes. So we're also developing algorithms that track the performance of your aircraft in real time and try to classify failures to things like we're in icing, my left aileron has failed, the battery's going bad, and still try to end these missions successfully. So with that, I'm going to look at these new, I think, exciting technologies. What kind of new Earth science missions are these leading to? So I have a couple examples here. The first one is a project that we first flew just almost 2 years ago now, and it was to collect CO2 off the shoulder of a volcano in Costa Rica. Now, that involved a lot of planning, a lot of work to make it safe and successful. Ideally, what this mission should do, and will hopefully do in the future, is a scientist could just go tell it, I want you to collect data 10, 20 meters off the canopy in this area. And they shouldn't have to be an aircraft expert, an operations expert. The aircraft should be able to find feasible paths and do that safely and automatically. And that's one of the, I think, upcoming technologies in the next little while. Going even one step further, sort of an exciting project that we hope to have flying in the next 2 years is where you're not only telling the aircraft where to fly. So this is, we're developing for NOAA disposable small drone to fly into hurricanes. And it's only a one-way communication system. So now we're not telling the aircraft where to fly anymore. We're telling it what kind of science we want it to gather. And the aircraft is, using all these technologies I mentioned earlier with the addition of using its onboard science sensors to plan paths to say, one example here is to autonomously basically fly around the eye wall at different altitudes. So to me, this is sort of going to be the next big leap where the aircraft are now making science decisions online. And that's, I think, quite exciting. The last one I'll mention is the commercial links. I think the commercial industry up till now for drones has been sort of focused on what I call the low-hanging fruit, photos, videos, land management. We're starting to see a big uptick in the commercial world wanting science-built drones and science-built sensors to really improve what they're doing. And the reason that's important is the commercial world funds technologies to be a lot more efficient, robust, and reliable, whereas the science world funds the technology just to get the science. So I think marrying these two industries together is just going to help both. And the last thing I'll mention is, since we're looking at sort of maybe the next 100 years, is I'd be willing to bet or wager that essentially every celestial body in the solar system that has an atmosphere, and we'll probably limit it to ones that could be modeled as continuum flow, so not those trace atmospheres, we'll have an aircraft flown it in by 2100. Now, NASA's already funding and has a Mars helicopter, Titan drone, and these are very exciting developments. Hats off to NASA for going after such ambitious missions. But I think but the takeaway here, the excitement to me is that this technology is becoming so reliable that we're trusting to send it to, send it all the way to another planet and trust that it will work. And fingers crossed it will work. I don't know if I have time for questions, but thank you.
Right, thank you. And now we're going to move on to Milton Hallam.
Well, first I'd like to thank our two hosts, Mike Seabloom and Jane Hart, for giving me the opportunity to present this talk. I will be presenting some new results just recently conducted that attempted to repeat an experiment that was conducted 50 years ago that justified the feasibility of a global observing system. I also want to thank my co-authors, Mark Kane, who also worked with me on that first experiment 50 years ago, and my student, Zhifeng Yang, who did most of the work today, and Richard Loft, who provided us with the most advanced model to conduct the same experiment that we did 50 years ago. Let me begin with a little historical setting. President John Kennedy, in his address to the General Assembly of the United Nations in 1961, proposed a cooperative effort for all nations in weather prediction and eventually in weather control. The National Academy of Sciences, shortly thereafter, in 1963, formed a panel of some of the most distinguished scientists, not just atmospheric scientists, nuclear scientists as well. And one of the chairpersons was Jules Charney. And one of the conclusions of that panel was the feasibility of a global observing experiment, that it would be possible with potential new observing systems to measure the complete state of the atmosphere. In 1969, NASA launched Nihms 3, carrying the first temperature sounding experiment, the Sears sounder, the Sears A, and shortly thereafter, the program manager from NASA headquarters visited the Goddard Institute of Space Studies in New York and requested from the group that was assembled there what can be done with temperature profiles. At that meeting was Jules Charney, Bob Jastrow. Fortunately, I was also present. And within 2 months, a paper was published titled "The Use of Incomplete Historical Data to Infer the Present State of the Atmosphere." It should be noted that even today, our observing system lacks the ability to measure winds. So there was a lot of concern at that time, whether it would be possible to put together an international program that would be able to provide the initial conditions for a global circulation model. I show in this chart 3 of the major results of that paper. The paper shows that this, by the way, was the first observing system simulation experiment ever conducted. It laid the foundation for future observing systems simulations. This is an identical twin experiment. It uses a model to generate what we would call a nature run. It introduces a perturbation after a certain number of days that grows up to generate new random states, and then it begins to assimilate what's the observed data or the nature run into the model. And so we see at these 3 charts, at mid-latitudes, there is an immediate adjustment of the model to winds at a very low level. In the equator, there seem to also be adjustments of the wind fields, and even the sea level pressure adjusted itself. This experiment was what one would call no proof of the feasibility that temperature sounding could do that, for many reasons. And it bothered Jules Charney that we were publishing this belief, which we call a rational belief, that this would be valid. He based his idea of this on the fact that if you have a system of first-order equations, you could reduce it to a single higher-order equations. And in linearizing the equations, he found that he could reduce it to second-order equations with a forcing term on the right, which consisted of the energy. That was his rationale, and he related it to the same problem of inferring the Earth's internal structure. It's an inverse problem, or scattering. But he also put a caveat on these results, and these appeared in the paper, what I'm quoting here. He said that we need to repeat these experiments with more levels. As I point out, the model that we used for this experiment was just a 2-level model, moisture only in the lower level, with the full physics. He thought that we just needed to do more resolution, more vertical levels. I'm going to report results that not only add more vertical resolution, more levels, but also new physics. And we'll be running, and I'll be presenting some results with multiple physics, microphysics, and new variables. One more thing on this chart I'll very quickly point out. At the Arakawa Symposium conducted by Dave Randall in the year 2000 at the retirement of Arakawa, I presented similar results with the Goddard GEOS model. And in that model run, which was 9 levels, we obtained similar extratropical adjustments of the winds, but very little adjustment in the tropics. The model I'm using today in the results that I'll be presenting is the model called MPAS, the model prediction across all scales, just recently developed at NCAR as their next generation community model. What's unique about this model, this set of equations, is that temperature is not a prognostic variable. What is the prognostic variable in this case is moist potential temperature. And the image that you see on the right is a Voronoi mesh, which actually can just shrink down to 1 kilometer or less, so that there is no boundary in this system. I'm going to report on the results of several experiments. One experiment, we used a 5-degree global 5-degree model, which we call 480 kilometers, with 20 levels rather than 2 levels. And all the physical parameterizations that you see on the right in this table, convection, microphysics. The microphysics is called WSM6. We also did another experiment with the Kessler microphysics. We did boundary layer physics, turbulence, cloud radiation, interactions, a Randall model, and gravity drag. We performed 4 experiments. One experiment was the insertion of temperatures, moist potential temperature. We did experiments with temperature as well, but time won't permit me to show those results. So I'll show the results of moist temperature, moist potential temperature, various errors. We did another experiment where we used a 240-kilometer resolution model to justify the results. And we did experiments with this other microphysics experiment as well. So on the left is the original description of the winds that were inferred just from temperatures in the original Min-Arakawa model. In the next chart was the use of the GEOS model. In the chart on the right, we're actually seeing in the dashed lines the perturbation run compared with the nature run. In all the other colors, the red, the blue, the green, and there's a purple as well. No, I don't think the purple is here. We see the adjustment of the winds at various levels, and you can see there's probably about a 40% adjustment in the winds from just the temperatures. At the equator, this is one of the more striking results of this experiment, which was very controversial in the early 70s, that the winds can adjust that in the tropics where we do not have geostrophic winds, where there is no adjustment to the Coriolis force, we are still getting an adjustment in the winds of about 40 to 50% in the equatorial regions. And then finally, we see a similar mild adjustment of the sea level pressure just to the moist potential temperature. Now I want to show the results, not of just the 500-kilometer run, but one with 2.5 degrees. So we call that the 240-kilometer versus the 480-kilometer run. And the blue curves are the 240 kilometers, and the red curves are the 500 kilometers. And here we're looking at the adjustment when we go to higher resolution, that we still see the adjustment of the winds, the zonal winds, on the right at 10 degrees latitude. This is at the equator. And on the bottom, we see it even in the southern hemisphere. On the right, we see the adjustment of the winds at mid-latitudes, and similarly at minus 50 degrees. And similarly at zero, you could see the large adjustment taking place at the higher resolution. This chart shows the sea level pressure at the equator and at high latitudes and in the tropics. But there was an interesting thing that was observed here at the higher resolution. If you notice the dashed line in the center chart in the middle shows a difference between the adjusted results when inserting the moist temperature compared to the perturbed results, an adjustment of almost 200%. What would explain that kind of an effect? So we surmise that might have been the fact that the moist temperature may have identified tropical depressions that that the perturbation run did not. And so we looked at the plot, and these experiments were conducted for over 150 days, from September 5th through January 3rd, from September 5th, 2018 to January 3rd, 2019. And I indicate here in the left, the nature run had an intense cyclone in the equatorial regions just off the Philippines and near in Indonesia. The perturbation run showed no such depression, but there was a slight depression just on the Philippines. And the theta insertion experiment captured the same result of the nature. Okay, so let me conclude the findings of this experiment. New microphysics and climate models replaces temperature with moist potential temperature. And this has an implication for future observing systems, that it's important to observe and incorporate moist potential temperature and data assimilation, especially in the tropics. In conversations last night with Mike Wallace, he expressed to me that moist temperature is more important in the tropics than the winds. Predictability limits for this model seem to be independent of scale. We looked at the growth rate of errors for 500 kilometers, 250 kilometers. We referenced a paper that used the same model at 4 kilometers, and the doubling rate was still 2 to 3 weeks. The observing system experiments, as I pointed out, showed wind corrections at 50 to 40% forced from the temperature data alone. And in particular, there is, even in the sea level pressure, we're still seeing 25% improvements in the inference, and in particular, capabilities of identifying tropical depressions. And so that's a review of an experiment conducted 50 years ago with today's most advanced model and most advanced computers, and has similar implications for global observing systems.
All right, thank you. Right, and now we have our final speaker, Rob Manning, talking to us about Mars.
Well, thank you, Mike and Jane. Thank you very much for inviting me. How much time do I have? About as fast as I can, huh? Yes. Okay. Okay. Let's see, where's the mouse here? Oh, right here. Okay, so I will speak fast, and some of you know me, I can actually do that. It's actually been 27 years of actual roving on Mars that's taken place so far. It's actually been less than 20 years since we've not had continuous 20 years of rover presence. But we've got a lot of experience, and we've gotten actually pretty good at it. And so this is really just a slow story about a little quick tutorial about what kinds of things that you can do with a Mars rover. And certainly, one of the things that revolutionized Mars surface science is getting ground truth of about 1/3 of a meter or so resolution we get from orbit. We also get it down to much finer scales. In fact, we were hoping to even be in the 100 micron or less scale coming up on our next Mars mission, which I'll talk about a little bit. Certainly, in situ analysis, enhancing exploration to really track from one place to another is I think has really revolutionized and we provided a sense of real exploration. That's something that if you built those who in the days we only had landers, it was nothing more frustrating to reach out, look out there in the image, and want to be able to touch units that you can't really get to without actually driving to it. So it's very frustrating unless you can drive. And so now, so we've had. Of course, many of you who think about rovers, they think about the technology involved in sensing, how these vehicles have to be fully autonomous. We only talk to them once a day, so they have to be able to do everything on their own. And we developed some very simple techniques back in the Sojourner days, back in 1997. We have since, with rovers since then, with Spirit and Opportunity, rovers, MER, Curiosity, and Mars 2020, which is launching in July. We've added, with stereo vision, and hazard avoidance, we're able to do a lot more path planning and be able to integrate this information with continuous imagery to actually do visual odometry, target tracking, approach and arm placement of the robotic arm, and we've even added hardware acceleration to make these things go even faster. Because actually, computer processing is part of the challenges in making a rover move. The rover has lots of other hobbies, though. Flying to Mars is one of them. Our rovers are in charge of entry, descent, and landing, which is a pretty complicated sequence of events, all fully autonomously, by the way. Certainly, robotic arm sample manipulation has to be done on its own. Imaging, remote sensing, in situ surface sensing, laboratory operations we did with Curiosity rover, autonomous communication, power and thermal control, many others, including fault tolerance, all have to be rolled into these machines. And as a result, these machines get really complicated. But there are key challenges. The first challenge that we have for all of our Mars vehicles is energy and energy efficiency. The second is mass and volume. But the trouble is our vehicles, they have to stuff themselves into a space capsule, and that space capsule has to be stuffed into a rocket fairing. And there's a limitation to how wide you can make these things. So we've found ourselves forcing our vehicles to be as tight and as small as we dare. We also have Mars unique challenges: diurnal, seasonal cycles, dust, rocks, slopes, and sand dunes. And the final challenge is figuring out all the technologies you need to help us deal with these challenges for 1 through 3. So that's our big one. So let's talk about the energy challenge very briefly. You have only two options for our rover on Mars, unfortunately, right now. You have to use what little is there at Mars, or you can bring your own energy with you. So if you're going to use the energy already on Mars, you really only have one option. Until the days our rovers can actually do some mining, actually do some more advanced in situ resource utilization, the only option you have right now is solar panels. And our solar arrays have been used on 3 out of our 4 rovers so far. The trouble with solar arrays, you need about 2.5 times as much solar arrays on Mars as you do on Earth for the same amount of power. And the arrays, and for example, the arrays on Spirit and Opportunity produce anywhere between 300 and 700 watts on a really good day. So typically around 400 to 500 watts. By the way, which is, about 20 watts on average over the course of a day. And this is watt hours, I should say. It's about 20 watts on average all day long. So imagine running a rover on 20 watts. That's not very much. What's more, you've got daily dust accumulation of about 0.25% per day that degrades the solar panels. And if you're lucky, you might get a wind-driven dust cleaning event, which happened maybe once every year or two on our rovers, Spirit and Opportunity. They were not guaranteed to happen, however. And in fact, the phenomenology is still not completely explained. Every 2 years or so, you get some dust storms. And if you and you can also you can try to clean off the dust that you accumulate for the dust storms. That's wonderful. You can try that. You can put mechanisms in plus. Maybe put some Windex out there. But the trouble is the sky can get pitch black, and if your sky is pitch black for months at a time or months at a time, no amount of cleaning of your solar panels is going to make a difference. The good news is that we've been able to track the solar array technology that's evolved. Terrestrial applications, the terrestrial technology has been going to Mars and helping us out. So the next option is bring your own energy. Certainly reactors and advanced Stirling radioisotope generators are still years away. And you can bring your own batteries, pre-charged batteries, and that's what Sojourner did. It brought a pre-charged battery, but it doesn't carry enough to last for months. So really you only have one option, and that is to use a multi-mission radioisotope thermoelectric generator, which basically is a very simple device. You put plutonium, you put lots of little tiny thermocouples between some hot plutonium in the middle and the cold air of Mars, and you produce electricity. Wonderful, about 100 watts of electrical energy. So a great big rover takes 100 watts of electricity. The good news is it produces 24/7, actually 24.47, because Mars' day is 24 hours and 39 minutes. 0.6, I should say. So producing about 2,500 watt hours of power per Mars day. In addition, this is really cool, you get about 2,000 watts of waste heat, which you can capture in heat loops and fluid loops and pump the heat back inside your rover. It's really cool. This is one of the biggest advantages of these RTGs. It's not the electricity, it's the heat. And we can and we don't have to worry about dust storms. It can get pitch black outside, and the rover will be perfectly happy. However, the bad news is they're very few and very expensive. So just point out that you can see the energy has improved over the missions. One thing people often ask is what fraction of the energy we use while we're actually roving. And it turns out the roving, while we're driving, we take roughly about 40% of the energy you need per soul to drive on a driving day. So about roughly between 15 and 50%. However, that part of that energy that's actually moving the motors is roughly between 5 and 20%. It's not a lot. So a lot of it goes in just actually running the computers, doing the software, doing the thinking. So being efficient is the most important thing for us. Don't hurry the science. 100 meters, which is, by the way, all what Sojourner did in its full life, is a big drive. And if you go too fast, a lot of scientists say, well, let's go back. We might have missed something. So we also sleep a lot. These rovers are asleep most of the time. 18 hours of the 24-hour day, they're sound asleep. So just point out that on a given day, a typical good day, we hope with the new rover to get somewhere around 250 meters per day. But most of our rovers have been less than around 100 or less per day. And Sojourner, the top speed was only top distance in a day was about 11 meters. And in fact, the total distance covered for these missions over the lifetime, Opportunity has the record at 45 kilometers. Curiosity is still at 21. It's still got a ways to go to keep up. So We have to do other things like keep everything inside a thermos bottle. Every lost watt to entropy is precious. Every extra watt we put into rechargeable batteries. We use passive articulate mobility suspension system to get the wheels on. We don't have to put motors or actuators for this. In fact, we steal an idea that was developed by Don Bickler in '88 and first used in Sojourner. It's called a rocker bogie system. It's basically a mobile. Or a whipple tree if you're into plowing and using oxen to pull your wagon. It's basically you take your vehicle and you make a mobile out of it, and you can see by articulating and have passive articulation. These this is greatly simplified. There's a little bit one more extra mechanism I didn't leave here. I left out here, but you can basically have wheels that can climb over a rock, a wheel height and diameter, which is something your car really can't do. Try it. Okay, so we've had an invasion of Mars rovers. We started with 11 kilogram Sojourner, we had 170 kilogram Spirit and Opportunity, and a 900 kilogram Curiosity rover, now working on Mars, still operating on Mars. This is what's next. No, I'm not. You can see the scaling, but we're not going to go to larger vehicles. The next rover is only about 100 kilograms or so heavier than Curiosity, but it's basically the same mission. What we learned in '97, really with Sojourner, it was really how to drive a rover. And driving a rover autonomously on another planet where you can only talk to it once a day, it has its own challenges. And so we learned a lot about that. Spirit and Opportunity rovers, which, as I mentioned, had very long lives. We basically learned how to be roving geologists, and not to mention the incredible satisfaction of discovering that Mars was a wet and warmer world 3.5 billion years ago. So with Curiosity rover, we learned something else. We learned how to be a roving geochemist with own laboratories to do in situ analysis on the surface of Mars of samples. That was a very powerful capability. It's a very different kind of mission because it moves very slowly. But the great thing is we've actually just convinced ourselves that Mars was habitable for life as we understand on this planet 3.5 billion years ago. Finally, we got Mars 2020, which is being built as we speak right now in Pasadena. It's fully assembled. We're doing some rework on it this week, in the next few weeks. And in a few months, it'll be shipped out to Florida, and we'll put it on our Atlas V and launch it to Mars. We hope to be able to see at finer scales ever before and collect samples for eventual sample return. So it's really this is basically a Curiosity rover with sample science and computer vision to enhance its speed to driving and the capability. So what's next? Can we build a rover that can safely traverse hundreds of kilometers? We don't know. It's really challenging. This energy problem's a big one. We need faster computers and more powerful sensors, for example, LiDAR, that require more power. But where will we get the more power? Can we use like a cheetah style of a rover where you do a lot in a day and get really tired and then sleep for 3 or 4 days, get your energy back? We could do that, but is that actually the more efficient way to go? We don't know. What about better instrumentation? We could really use some isotopic analysis for age dating and other techniques, but we don't have that. It's not small enough to fit in our vehicles and low enough power. What about better mobility? Can we get access to steeper slopes and cliffs? This is the next frontier, and I hope that some of you will be able to participate in that. Thank you. That was a fast talk. Did I catch up?
Right, thank you. Thank you for everyone who's attended the session, and to all the speakers. That was a really interesting session. I'm sure the speakers will stay around during the coffee if you've got any questions for them. But let's have a final round of applause for our speakers this morning. Thank you.